Okay, students, good morning. Am I audible?
Good morning, sir.
Good afternoon, sir.
Yeah, good afternoon.
Good afternoon.
Mm, how many classes do you have? Did you have today?
Total 5 classes.
So including
Three.
this one, this is the fifth class.
Mm,
Hmm.
This is
No,
the third class.
yes, also, sir.
This is the third class. Okay.
After this, there is another, sir.
From what time?
From 2 to
2 to 3:30.
3.
2 to 3. Okay. Okay. So let's start for today's class. The syllabus that I am going to start here is I will start module 2. Okay. And module 2 is about transistors or BJT. So I will start with the book. Okay.
Yes, sir.
Mm. So I am sharing the screen. Okay. So this I hope it is visible. So this is from the same book, chapter number 3, electronic devices and circuit theory by Bolstead. Okay. So I also encourage you to refer to this book. Okay, I have told already in the very first class that this is the book. This is also there in the textbook list. Okay, and is a very good book, standard book, so you can follow. Okay. So about the introduction part, uh, look before BJT actually. Before BJT, vacuum tube was popular. Okay. Uh, Vacuum tube based diode, or something called as triode. Triode was having 3 legs, and diode, vacuum tube diode, was having 2 legs. Okay. So this one. So before BJT, vacuum tube based diodes and triodes were popular, and they were actually used in around the world. So like the production rose from about 1 million tubes in 1922 to about 100 million tubes in 1937. So this is pre-BJT era. Okay. Okay. But in 1947, okay, these three scientists, Dr. S. William Shockley, Walter H. Brattain, and John Bardeen. Okay, they demonstrated the amplifying action of the first transistor at Bell Telephone Laboratories. Okay, and from there BJT took over this vacuum tube, and because of several reasons. The first reason was that BJT was smaller in size as compared to vacuum tube. Okay, it consumed very less power as compared to vacuum tube. The noise was less. Okay, the size or the space that it took was less. So the advantages were obvious, and because of that, this BJT became popular, very popular in a short span of time. Okay. So let us come to the construction of BJT. Look at here in this diagram. Look at here in this diagram. So we have, look, BJT is a 3-terminal device. With BJT, or bipolar junction transistor, bipolar junction transistor is a 3-terminal device, whereas diode was a 2-terminal device. Okay, so in diode we had just two terminals called as anode and cathode, but BJT has 3 terminals. And because it is having 3 terminal, so it can be applied to more variety of applications. Okay, and the utility of BJT becomes more as compared to diode. Why? Because it is having more number of legs, more number of terminals. So it's a 3-terminal device which is more useful than a 2-terminal device or diode. Okay, look at here. So it also consists of 3 layers. Okay, so this is the first layer, P. This is the second or the middle layer, N type, and the third or the last layer, P type. So it's a PNP transistor. Okay, and these are the typical thickness. The thickness of the middle region is around 0.001 inches. Okay, and the total thickness may be around 0.15 inch. So it's obvious that the thickness of the outer regions, these two P regions, are very high, are more very high as compared to the thickness of this middle region or base. So this E stands for emitter, this B stands for base, and C stands for collector. You might be aware of these terms, but still. So emitter, base, and collector are the 3 terminals. So what are the 3 terminals of BJT? Emitter, base, and collector. 3 terminals, no? E for emitter, then B for base, and C for collector. And why are these called as emitter, base, and collector? This will become clear as we go through the working of the BJT. So we have 3 layers, P, the first layer P, the second layer N, the third layer again P. So we can also call this as P emitter, region, N base region, then the last P collector region. But these are basically the terminals which are coming out from the transistor. So this E terminal is coming out from this emitter region, is connected to this wire, and is connected to a battery like this. Similarly, the base terminal is connected to these 2 batteries like this, and the collector terminal is connected to this battery. Okay. Okay, and how are these batteries connected? We will see. So basically the structure is like this. We have 3 layers of semiconductor. One is P, then the middle one is N, the outer one is again P. The middle layer is the thinnest layer. Okay, and the doping of these 3 layers are also different. Look at here, the doping of the sandwiched layer or the middle layer is also considerably less than that of outer layers, typically 1:10 or less. So the doping of this base would be 1/10 or even less than the doping of these emitter or collector regions. Okay, and the thickness of this base region is also small as compared to the thickness of these outer regions. So keep these things in mind. Okay. And why it is called a bipolar transistor? So it's bipolar. Okay. Bipolar reflects the fact that holes and electrons participate in the injection process into the oppositely polarized material. That is, both types of charge carriers, that is holes and electrons, participate in the current flow. So bipolar. Okay. And there are some devices in which only one type of carrier, when if only one carrier is employed, either electron or hole, it will be considered as a unipolar device. Okay. So for example, this Schottky diode is a unipolar device, but this BJT, because here holes and electrons both will be contributing in the flow of current, and because of this it is called as a bipolar junction transistor. Bipolar. Okay. So we can also have, similarly we can have instead of PNP we can have NPN transistor. Okay. So outer two layers are N and the middle layer is P, so it becomes NPN transistor. So this is basically NPN transistor. And the other things are similar, that is the middle layer or the sandwich layer is thinner, very thin as compared to outer layers, and is also very lightly doped as compared to the doping of outer layers. Okay. And rest of the things would remain same, that is, this is the emitter terminal, this is base terminal, this is collector terminal, and also the biasing, the way in which we bias these two junctions would also be opposite. Okay. Look at here. So this is N, this is P. Okay, so we have a junction, PN junction here. This is the first PN junction. Okay. And and this is in between base and emitter, so we call this as base emitter junction. Okay. We have another junction between base and collector, which is this one. This is the second PN junction, so we may call this as collector base junction, or CB junction, C for collector, B for base. Okay. And similarly this can be base emitter or emitter base, BE junction or EB junction, right? So the point here is that we have two junctions inside this BJT. One is base emitter junction and the second is collector base junction. Okay. And we know that one junction, one PN junction means one diode, right? So in a very crude way we can say that the BJT consists of two diodes. Although when you connect two discrete diodes, it will not act as a BJT device, but internally if we look at the structure, we can say that since there are two junctions inside this BJT device, so we can say in a very rough sense that okay, it is a kind of interconnection of two PN junctions or two diodes. Okay. So this is the thing, and we know that when we have a diode or a PN junction, we can provide two types of biasing to that diode. It can be either forward biased or reverse biased. So for each of these two junctions, base emitter and collector base junctions, each of these two junctions can be either forward biased or reverse biased by connecting the external batteries. Okay. So we have several choices. So what type of biasing is suitable for what kind of operation will become clear. That is also a kind of that is also to be taken care of. Okay, to use this BJT as a proper device, in constructing the circuits. Okay, so look at here. The first diagram, this one. So we have a this is P and this is P and P BJT. So I will write here. I can write this is P, this is N, this is P. A PNP BJT, a PNP transistor. Okay. So what it has done, it is shown in the figure that the first PN junction, this one, the first PN junction between the emitter and the base. So a battery is connected, called as VEE. So a battery is provided, VEE is provided to bias the emitter base junction. Since this is P and P is connected to positive terminal of the battery, and N base is N is connected to negative terminal of the battery. So this emitter base junction is forward biased. This emitter base junction is forward biased. EB junction is forward biased. Okay. So this is the first junction, and in second figure, okay, okay, and the second junction is just left out. It is not connected. It is open circuited. So it means that the second junction, because this is not connected, so current will not flow in this loop. The current will be 0. Okay. So this is of no use with this kind of connection. So it is just about the emitter base junction, right? Okay, let me connect the charger. Okay. And similarly, here in figure B, the first junction is open circuited, so current in this loop is 0. Okay, but there would be a current in the second loop, because the second junction, that is because this is P, N and P, the P side is connected to negative and N side is connected to positive. So this collector base junction is reverse biased. Okay. So what they are showing here is the first junction is forward biased in figure A, and second figure, that is B, the outer junction or the collector base junction is reverse biased. And there is a motto behind this, okay, because we generally use transistor, we generally bias transistor in such a way that emitter base junction is forward biased and collector base junction is reverse biased. Okay, and that is why it is being shown here. Look, when the emitter base junction is forward biased, the current will flow because of the majority charge carriers. We know about this from the functioning of the PN junction diode. Okay, and the current flow would be in this direction as shown by this arrow. Okay, and the thickness of the depletion layer will decrease because this is forward biased, right? So there is a current flow in this direction, that is here, and base current is coming out here. Okay, here in the second figure, that is in B part, since this collector base junction is reverse biased, so the depletion width will increase. Look at this black shaded region, this one. This is the depletion region which has increased because of the reverse biasing that is being provided from VCC. And we know that when the diode is reverse biased, its depletion layer increases. But there is a small current flowing through this junction, which is because of minority charge carriers. Okay, and the direction of that current would be like this, as shown by this arrow. And we also know that this is called as reverse current or reverse saturation current, because the current value is almost saturated, that it will be constant with respect to the change in the value of VCC. Okay, but the value of this reverse saturation current will be very small as compared to the current when it flows through a forward bias diode. Okay, we are aware of these facts. So in one figure, the base emitter junction is forward biased and big current flows. In second figure, the collector base junction is reverse biased and hence very small current flows. Okay, so keep these things. This is nothing new that we have shown here. We have just used our previous knowledge, okay, about diodes. Okay, now come here. So let me, yeah, this is fine. So let us combine those two conditions. Okay, so here VEE is making this emitter base junction forward biased, and this VCC, okay, is making the collector base junction reverse biased. So in this case, VEE, the function of VEE is to make emitter base junction forward biased, and the function of VCC is to make the collector base junction in reverse biased mode. And because of this, the thickness of depletion layer for collector base junction will be more as compared to the thickness of depletion layer for emitter base junction. Okay, so these two are the scenarios, and we had seen that the current flow was actually in the same direction. Okay, so if you can see this if you can see this blue colored arrow, thick arrow, okay, this one, and this is the current flowing because of majority carriers, okay. Now in the figure A, only because emitter base junction was forward bias and collector base junction was open, left open, the current was flowing in this loop only. But here we have connected biasing to both of these junctions. So what happens when majority carriers from P side, which are actually holes, enter into the N type base region, and keeping the fact that base region is very thin, okay, and is also very lightly doped, so it is out of the capacity of base region to hold these majority charge carriers for a duration of time, okay. And we have connected VCC, which is making this collector base junction in reverse bias mode, and the polarity of this VCC is such that it will attract the positively charged holes coming from P towards N, and they will jump this depletion region and enter into the collector region, okay. So the holes coming from emitter towards base will enter into collector, and this is why it is shown like this. The arrow is shown like this, from emitter towards collector, okay. But a very small portion of this will deviate from this direction and will travel through this base terminal, okay. And that is why this, look at this, at the bottom side I am drawing a thin arrow, this one, okay. So it signifies that a very small portion of this majority charge carriers will deflect away from this direction, from emitter to base, and will get deviated towards base terminal and will form the base current IB, this one, right, okay. So we had this thick arrow going from emitter towards base, okay. Most of the portion went into collector, and a very small portion got deflected, and then came out through this base terminal. This is the first scene, okay. This was arising because of this VEE biasing. Now VCC is also here, which is making this collector base junction reverse biased, and we already saw that when it is in reverse bias mode, the minority carriers will come into picture, and because of this the current will flow in this direction. Look at this arrow at the top side, this arrow coming from base towards collector, okay. We had only these two currents now. One was this because of minority charge carriers, and one was this because of majority charge carriers. Class okay. And the only change that is here is the deflection of some of the majority charge carriers from this big arrow towards this base terminal, okay. That will form the base current, okay. And because the deflection is very small, the number of charge carriers which are coming to this base terminal is very small, the magnitude of IB will be very small as compared to the magnitude of IE and IC, okay. So now the direction of IE, IB and IC are clear. So if we assume that this device is a meeting point for IE, IB and IC, and you apply KCL, we can easily write that IE is equal to IB plus IC, okay. That is, the emitter current is equal to the sum of base current and collector current. Okay, this is a very important relationship. Always keep always remember this. And this condition is valid for all kinds of BGTs under all, under any kind of situation. So this is valid in under all circumstances. This is the outer scene, but internally this is the scene that there are current because of majority charge carriers and minority charge carriers. Their directions are same. Some charge carriers, some majority carriers are getting deflected from the main direction towards base, and they form the base current. Okay, this IE and IC will be in the range of milliamperes, and IB will be in the range of microamperes or nanoamperes, okay, depending on the type of BJT. Right? I hope this is clear.
Yes, sir. Yes, sir.
Okay, so this can be explained with the explained for NPN transistor also same in a similar fashion. Okay, so what is shown here? Okay, for NPN transistor only the direction of currents will change. Okay, the direction of currents will change because we have changed the type of materials. Earlier it was PNP, now it is NPN. So the current directions will change. The biasing voltages will also get reversed, but the explanation of the functioning of that BJT will remain same. Okay, so basically this one. This one. So about symbol, so this is the symbol. Let me draw the symbol for a PNP transistor. So we have like this. This is NPN transistor. Okay, it's a 3-terminal device. So this is base, this is collector, this is emitter. The differentiating thing between collector and emitter is that there is an arrow over emitter terminal. So this arrow is pointing outwards for the case of NPN transistor, NPN BJT, and it will point inwards for PNP transistor. This is PNP BJT. Okay, this is more clear here in the figure, in this figure actually. Look at this. This is the base terminal, this is emitter terminal, and this is collector terminal. The base terminal is in between emitter and collector always, right? So we have two terminals, two auto terminals, that is emitter and collector. Okay, now the arrow, look at this arrow. This arrow is pointing inwards, so it is a PNP transistor symbol. Okay, and IE, the current of the emitter current direction will be in the direction of this arrow. So this arrow is actually signifying the current direction for IE, emitter current. So this is going inward, and IE is equal to IB plus IC. So IB will come out, IC will also come out, so that this KCL condition, that is IE is equal to IB plus IC, is satisfied. That is this one. Okay. Yeah, one more thing, that is the current, collector current IC. Let me go to the this one. Come to this figure, this one. The collector current IC, okay, was because of two factors. If you remember, we had just discussed that it was because of majority and minority charge carriers. The majority charge carriers were coming from the emitter side, okay, because this emitter base junction is reverse forward biased, okay, and the minority charge carriers was coming from this area itself, because this collector base junction is reverse biased, okay. So this IC consists of two parts, IC majority plus ICO minority. Okay, this ICO is actually uh, read like this: ICO, IC current with emitter terminal open. So remember, in the very first figure we had only this biasing present, and this was left open, emitter base junction was open. In that situation, the reverse current that was flowing in this loop was called as ICBO, that is the current from base, ICBO, current between collector and base when emitter was open, or in short it is also called as ICO. IC current, C for collector, IC current when emitter terminal is open, O for open, okay, emitter terminal is open. So IC current with emitter terminal open, and this is because of the minority charge carriers. So IC is equal to IC majority plus ICO minority. And always remember that this minority charge carriers, or the reverse saturation current, okay, in this case would be very 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 small as compared to this IC majority. So we can very safely write that IC would be IC majority if we ignore this IC minority, and it can be done for many practical purposes, okay. So the because this transistor is having three terminals, so there should be a certain way in which we can use this transistor, okay. So it is having emitter, base and collector. It is having three terminals, okay, and the symbol is, let's say, this one. So which terminal should be connected to the input side, which terminal should be connected to the output side, and there is one more terminal, the third terminal, how to use this. So there are certain configurations, okay, in which we can use this transistor, or in which we can use this BJT for our applications or for constructing various circuits, okay. So the first type of configuration is called as common base configuration. Common base, the name suggests that the base terminal is common. Common to what? The base terminal is common between input side and the output side. That is, base is common between input and output. Input and output ports, or input and output side, okay. So no, Yes, this one. Look at this diagram. This one. The base terminal is grounded. Is grounded. Okay, is grounded here, connected to ground. The emitter terminal is connected to this VE, and the collector terminal is connected to this VCC, right? So this base terminal, which is grounded, is commonly available for the input side as well as for the output side. Okay, so this is the input side and this is the output side. So if we look from the input or output side, we will see base terminal in both cases. Okay, so this is the connection for a common base. This is common base. uh, Configuration. Okay, but remember that the input junction, that is emitter base junction, is forward biased because of VE, and collector base junction is reverse biased because of VCC. And for making amplifiers, this is the scenario, this is the this type of biasing we use generally. That is, the emitter base junction is always forward biased and the collector base junction is always reverse biased. Okay, for making amplifiers, right? Okay, now so this is the connection for common base configuration for a PNP transistor. Okay, similarly we can have common base configuration for NPN transistor also. Okay, look at here, the base terminal is connected to ground, and this is NPN and PN. So the emitter base junction is forward biased because of VE, and base collector junction is reverse biased because of VCC. Again, this is the input side and this is the output side. This is the input side, this is the output side. Okay, so now look at this scenario for common base configuration. Okay, now the thing is to analyze this circuit, to analyze this configuration. So remember, we will have common base configuration. Okay, we will have common emitter configuration, and we will also have common collector configuration. We will have all these three types of configuration, but let's start with the first one, that is common base configuration. So this is the circuit for a common base configuration, right? So there are various types of current and voltages in this circuit. We have IE, IB, IC, VEE, VCC. Okay, and if we look the voltage between emitter and base, we will have VBE, then we will have VCB, that is the voltage between base and collector, VCB. Okay, so there are various voltages and currents in the circuit, and in order to properly explain this configuration, or in order to properly analyze or to study the properties of BJT, we need certain types of analysis. And for those purposes, there are two sets of characteristics which are there, which are used to describe the behavior of BJT, which are sufficient for describing the behavior of BJT, and those are input characteristic and output characteristic. Okay, so we have input characteristic and output characteristics. So we have two sets of characteristics, input characteristics and output characteristics. Okay, and this is the figure for input, or also called as driving point characteristic, for a common base silicon transistor amplifier. So just for convenience, I will draw the common base. Okay, let's NPN, let us take NPN. So arrow is pointing outwards. So this is the transistor, this is NPN. Okay, this is NPN. The arrow will define which type of transistor it is. This is NPN transistor. Okay, so N is connected to negative, P is positive, it is forward biased. Here the collector side is reverse biased, N is connected to positive, and then like this. The base terminal is connected to ground. Okay, so this is emitter, this is base, and this is collector. This is the direction for IE, and this is the direction for IB and IC. Let's call this as VEE and VCC. Okay, now look at from the input side. So that input characteristic is a plot between input parameters, that is input current versus input voltage, VBE versus IE. IA, input terminal is emitter terminal, and the current flowing in this terminal is IE. So this is input current, and VBE, that is the input voltage. When you look from the input side, the voltage that appears between emitter and base, this is the input voltage. Okay, so IE versus VBE for different values of output voltage, and output voltage is this one, VCB. That is the voltage that appears between base and emitter, base and collector, when you look from the output side. So input current versus input voltage for various values of output voltage, VCB 1 volt, VCB 20 volt, or VCB 10 volt, whatever. Okay, now look, the input IE versus VBE, the input is what? The input side is what? Is actually a junction, is actually a PN junction, which is forward biased because of VEE. So when we are plotting input current versus input voltage for this input junction, which is actually forward biased, so we can guess that the characteristic curve will come similar to that of a forward biased diode, right? And that is why you see this type of characteristic curve, which is similar to the curve for a forward biased diode. Look at this, the first case, when VCB is equal to 1 volt, when the output voltage is 1 volt, the curve is like this. Okay, which is same as the forward biased diode, IDVD curve, right? So it starts from 0, remains almost 0, right? And at a certain particular voltage, it starts rising exponentially, and let's say this is 0.7 mark. So at this point, the value, the voltage, the value of the current is around 1.5 milliampere, and then when we go beyond this 0.7 voltage, the current increases very rapidly. So around in this region, it has started to, come up. It has started to rise. So from this, we can actually guess the knee voltage for this particular. Or this is not a diode, but if we refer this as a diode, and remember the fact, although I am saying that it consists of internally two junctions, so we can very roughly, again I am saying, we can say roughly that it consists of two diodes, but it is not. When you practically connect two separate diodes, and you expect that connection works as a BJT, it will not happen. Okay, the same, the two junctions are actually formed on a single silicon, single silicon piece. So this junction and this junction, they are formed on the same wafer, on the same silicon piece. Okay, they are not combined separately, so they are constructed intrinsically. Okay, we are not connecting any two junctions separately, although, but rather they are formed or produced on the same silicon crystal by using the techniques. Okay, so because the first junction is forward biased, so the input characteristic between input current and input voltage comes similar to the characteristic of a forward biased diode, like this, when VCB, or when the output voltage is 1 voltage, let's say. Okay, when output voltage goes more, rises more, becomes higher, that is, if we increase the value of VCC, then VCB will increase definitely. So let's say 10 voltage. Earlier VCC was something lower, so that VCB was actually 1 voltage. Now we increase the value of VCC, so VCB became 10 voltage. Okay, if the output voltage is going high, then what will be the effect? The majority charge carriers, which are actually coming from the input side, that is the emitter side, okay, will be collected from the collector, will be cached from the collector side with a higher intensity of electric field, because we have increased the value of VCC from 1 voltage to 10 voltage, 10 times stronger, right? And because of this, the value of current flowing would be more inside this BJT, and hence you see that the curve for VCB is actually here. Okay, let me is actually on the right side, sorry, left side, as compared to VCB when it is 1 voltage. So at a particular voltage, let's say at this point, if I draw a perpendicular line, and if I compare the value of current when VCB is 1 voltage, it is around 4 milliampere, and when VCB is 10 voltage, it is around 6 milliampere. So the value of current is rising, and similarly when VCB is 20 voltage, it will become even more. Okay, but the thing is, because the input biasing voltage will not vary much, it will be around in the range of 0.7, 0.8 something. Mostly it will be around 0.7 voltage. Okay, so this variation does not matter much, although there is a variation, there is an increase in current with increase in VCB voltage, right? So the points are the curve or the input characteristic curve between I and VB will be similar to the curve for a forward bias diode, because this input PN junction is forward biased because of VEE, right? So this is the input characteristic for a common base diode, and we also have the output characteristic for common base BJT. Look at here. So this is the output characteristic, also called as collector characteristic for a common base transistor amplifier. This is the curve between output voltages and output current. Output voltage is VCB, and output current is IC. So VCB versus IC. A plot between IC and VCB for different values of input current. And what is the input current? Input current is IE. So it is the first, this is the first blue line is when I is equal to 0 milliampere. This line is when I is equal to 1 milliampere. This is when I is equal to 2 milliampere. This is when I is 3 milliampere. This is when I is 4 milliampere, 5, 6, 7, and like that. So for different values of input current, the curves are plotted. Okay, and this forms the output characteristic for this common base configuration. So output current versus output voltage. So here they have shown three regions. The first is cutoff region, which is, as the name suggests, the region is cutoff, means there is no current flowing. So when I is 0 milliampere, or when input current is 0 milliampere, this is the curve, which is almost equal to 0. The value of IC is 0, right? And below this region is your cutoff region. So in cutoff region, basically the current is 0, right? Now this is the for horizontal axis, x-axis, this is the 0 mark. So actually this is the line, vertical line. This is the vertical line. Okay, and this is -1. This is 0. So the scale on the left side of 0 is expanded to make the things visible more clearly. So what it is trying to show is that there is something called as saturation region, which exists on the left hand side of for this VCB is equal to 0 voltage. That is this region. And what happens actually in this region is that the current, that is this IC, actually rises exponentially. Okay, look at the first, when I is equal to 1 milliampere. So this is coming here like this, and it was actually like this. The second curve is almost constant in this region. It is not changing much. But before, when it actually rose to this maximum value, it was coming from this very low value, and this rise from this low value to high value is almost instant, exponential rise. Okay, so this region suggests that the point at which the IC rise to its maximum value and it remains constant, it does not change. Okay, so the point at which it just rose and then afterwards it remains constant, so that is, it reaches its saturation value, it reaches its maximum value. Okay, so that particular region is described by this, called as saturation region. Okay, and then in between cutoff and saturation region we have this active region. Okay, and this is for amplification purpose, this is the most important region. So this complete unshaded region is the active region. Okay, and this is where amplifiers are built. So amplifiers are built in active region, remember always. And digital circuits which works on binary pattern 0 and 1, 0 means off or 1 means on. So cutoff means 0, saturation means on. So digital circuits are constructed by using cutoff and saturation region. So I'll write here, digital circuit uses cutoff and saturation, and analog or amplifiers uses which region? Active region, right? Okay, so this active region is of utmost importance as far as amplifiers are considered. Okay, so what is there in the active region for any case? So for example, this one, in active region the curve is remaining essentially constant for a sufficient duration of sufficient value of sufficient range of VCB. So with respect to VCB, the value of IC is not changing, it's constant, essentially constant. So it means that the output voltage change is not having any impact on the output current for a sufficient range, 0, 10, 20, 30, 40. Okay, this is the 40 mark, 40 voltage mark. And this is a practical device, we know that this will have its limitation. So after a certain value this starts going up, all these curves. Okay, so there we decide that okay, now this is the point, this is the boundary, this is the limits, so we should operate our device before, before this point, that is in this region. If we want to utilize active region, it should be between this point and this point. When it actually starts to go up, there it will go up and the current will increase so much that it will get burned up, it will burn. Okay, so we should take care of this device when we use it in active region, that is it should be used within the prescribed maximum current levels. Okay, it will be mentioned in the data sheet of the device itself, but from the graph we can see the behavior here like this. So in active region the current remains essentially constant with respect to output voltage, and the value of IE, look at here, this is IC, right? For example, this case, this is when IE equal to 3 milliampere. So for this curve the IE is 3 milliampere, and what is the value of IC? So when we go like this, when we project this line, it will come just around 3 milliampere mark. This is in milliamperes. And similarly, if this is I 6 milliampere, it will come around 6 milliampere. So from this graph also we can say that the value of IE is almost equal to value of IC, but actually IE is equal to IB plus IC, but because the value of IB, the current of the value of base current is so small that we can neglect this IB for many purposes, for many applications. Okay, but not in all the conditions. We can use this condition, we can write this condition for simplification purpose, and this is also visible from this graph. Okay, so this is the output characteristic for common base configuration, right? And then I will encourage you to go through this section in this book. Okay, and there is one more parameter which is left. So there is one parameter called as alpha, which is defined for common base configuration. Alpha is the current gain, which is the ratio of IC by IE. IC is the output current, look at from the diagram. IE is the input current. So output current by input current is nothing but current gain. So alpha is the, if alpha DC is the DC current gain for common base configuration, called as alpha. Okay, and this is for the majority carriers. So when we take into account the minority, carriers also, we know that IC was IC majority plus ICO minority, right? And from the definition of alpha, IC becomes alpha DC times IE. So IC is actually equal to, and this alpha definition is for majority carriers. So IC becomes IC majority. So this is IC majority, that is alpha IE plus ICO minority. But again, this term can be neglected for almost all applications. So you will see that the definition of this alpha is simple IC by IE, will be used in all the numericals, and this would be 0 unless otherwise it is stated to take this parameter into account. By default we will assume that this ICO is 0. Okay,
Sir,
yeah,
sir, can we continue from tomorrow? Sir, we have another class and we haven't taken the lunch yet.
yeah, I'm just ending, I'm just at the end, right? So this was about common base configuration, right? So you go through this section, and the definition for alpha AC is same, IC by IE, and it is for AC, so it is the ratio of change in IC by change in IE, nothing much. Okay, and for all practical purposes we can choose the the value of alpha DC is actually equal to alpha AC, so we can interchange these values, the values are similar. Okay, so do not worry much about alpha AC, alpha DC. Look at the definitions, the values are actually similar to each other. Okay, so with this your common base configuration is open, common base configuration is over, and then we will start in the next class the common emitter configuration. Okay, right, so I will take the attendance quickly, just here, just a minute. Today is 27. Okay, class. So respond to your attendance. Roll number 1,
Present, sir.
roll number 2,
Present, sir.
roll number 3,
Present, sir.
roll number 4. Sumit Panigrahi, absent. So those who have given attendance, they can leave. Okay. Roll number 5,
Yes, sir.
roll number 6,
Present, sir.
roll number 7, absent. Roll number 8,
Present, sir.
roll number 9,
Present, sir.
roll number 10,
Present, sir.
11,
Present, sir.
roll number 12,
Present, sir.
roll number 13,
Present, sir.
roll number 14, Aditi Jalan. Okay. Roll number 15, absent. Roll number 16,
Sir, 15 present.
okay, 15 present. Okay. Roll number 16, Vaibhav, absent. Roll number 17, absent. Roll number 18,
Present, sir.
roll number 19,
Present, sir.
roll number 20,
Present, sir.
21,
Present, sir.
roll number 23,
Present, sir.
roll number 24,
Present, sir.
roll number 26,
Present, sir.
roll number 27,
Present, sir.
roll number 28,
Yes, sir.
roll number 29,
Present, sir.
roll number 30,
Present, sir.
31, roll number 31, Amlan, present, absent. Roll number 32,
Yes, sir.
roll number 33,
Present, sir.
roll number 34, Chirag, absent. Roll number 35,
Present, sir.
roll number 36,
Present, sir.
roll number 37,
Present, sir.
roll number 38,
Present, sir.
roll number 39,
Present, sir.
roll number 40,
Present, sir.
roll number 41,
Present, sir.
roll number 42, 42, Smruti Neha Raul, absent. Roll number 43,
Present, sir.
roll number 44,
Present, sir.
roll number 45, roll number 46,
Present, sir.
roll number 47,
Yes, sir.
roll number 48,
Present, sir.
roll number 49,
Present, sir.
roll number 50,
Present, sir.
roll number 51,
Present, sir.
roll number 52, Abhishek, absent. Roll number 53, Devashish Kar, absent. Roll number 54,
Present, sir.
roll number 55, Kishan Kumar Samal, absent. Roll number 56,
Present, sir.
roll number 57,
Present, sir.
roll number 58,
Present, sir.
roll number 59, Priyanka Chaudhary, absent. Roll number 60,
Present, sir.
roll number 61,
Present, sir.
roll number 62,
Present, sir.
roll number 63,
Present, sir.
roll number 64, Shashwati, absent. Roll number 65,
Present, sir.
roll number 66,
Present, sir.
roll number 67, roll number 69, Prabhu, absent. Roll number 70,
Present, sir.
roll number 71,
Present, sir.
roll number 72,
Present, sir.
and Pitambar, absent. Okay, class. If you have any doubts, you can ask, or else you can leave the class.
Thank you, sir.